Alright, so heat is not the only way that energy can be transferred. Work can also happen. And so we have this nice little equation down here. Work is equal to the negative external pressure times the change in volume. So essentially what we're saying is if a chemical reaction is doing work, it's pushing against the atmosphere and creating a volume change. So when work is done by the system, volume is going to increase. Now, why is this important? Well, we have this thing called bomb calorimetry. And now this is how we figure out the calories in food and such. Now, internal energy is heat and work together. But to do work, you have to change the volume somehow. So what we do with bomb calorimetry is we keep the volume from changing. We hold volume constant intentionally. And so what ends up happening is, since no work can be done, all of the work comes out as heat. Okay, so this is why we have the QV, because that is heat at constant volume. And so if all of the energy comes out as heat, and we keep track of it in a bomb calorimeter, we can then say, okay, well, whatever heat was absorbed by that calorimeter system, or the calorimeter, it's the surroundings in this case, the opposite was given off by the reaction. And so if we figure out the heat of the reaction, then that is Q at constant volume, which is the internal energy of the reaction. So all three of these equations down here are important. These two right here are kind of common sense if you can think through what's actually happening. This one is the equation that you'll definitely want to remember. So let's look at a problem. You got 1.10 grams of sucrose. You burn in a bomb calorimeter. You get the change in temperature. Find the internal energy change for that reaction. We have the heat capacity of the bomb calorimeter. So, first of all, internal energy is reported in kilojoules per mole, so keep that in mind. Our equation said that Qcal is equal to Ccal times delta T. So in this case, that would be 4.90 times final minus initial is 28.33 minus 24.92. So let's see here, 28.33 minus 24.92. 3.41, and then you multiply by 4.90. So your Q here is 16.7 kilojoules. Now here's another thing to keep in mind. With Q equals mc delta T, you have joules, but here we have the calorimeter constants in kilojoules, so our answer is in kilojoules. Now this is kilojoules per 1.010 grams. So if we want to find kilojoules per mole, we're going to have to do a conversion. So we got 16.7 kilojoules. That was for 1.01 grams of sucrose. Well, there are 342.3 grams in 1 mole. So I do 16.7 divided by 1.01 times 342.3, and you get 5,600. We're looking at what? I guess that's a constant. I don't know. If we'll just stick with 4 sig figs for now, it might be 3. That would be kilojoules per mole. And then, since this up here was positive, it's going to have to be negative for the reaction. So, because we switch, Q cal is equal to negative Q the reaction. So that is all there is to that. Hopefully that was helpful.